We can hear you now.
Octavio, can you hear me?
Yes, we can hear you.
Okay. Okay, very good. So I will add Octavio as co-host. Also the second Octavio. Yes. And my surface. Anyway, Octavio, I think you can start.
Okay, I can start.
Yeah.
So what we're gonna be doing today, it's so I'm gonna show you a number of exercises that I prepared on certain topics that are going to be similar to the ones in the exam. And then the professor is going to show you another set of examples that he prepared himself. And then he also prepared, like, he's going to show you some questions that might be similar to the ones that are going to be in the exam. Please feel free to interrupt me if you don't understand something, or if you see something that doesn't make much sense. You can always interrupt me. This is supposed to be helpful for you, so if there's something that is not clear, please let us know. So let me share my screen now. Okay, give me 1 second. Okay, now, okay, see how I can do this. Okay, so share screen. Okay, share. Okay, you can see my screen now, right? Michele?
Yes, yes.
Okay.
Everything's there.
Okay, good. So the first exercise that I prepared, it's a fairly simple one, which is going to be on the topic of sensors. So here in this one, I took we're going to be using sensors that actually exist. And the idea of this kind of exercises, these problems are quite simple, but these are kind of things that you will be facing in the, let's say when you're selecting a specific sensor for a certain application. So I'm gonna read out loud the exercise, and then we're gonna look at the data that we have in the exercise, and then I'm going to proceed to solve the exercise. So the exercise reads: consider the magnetic incremental encoder shown in the next slide. I'm going to show you afterwards the next slide. In the sensor is an RSL RM44, and the data sheet of the sensor indicates a 13-bit resolution. And we're considering this encoder to measure the joint positions and velocities for a robot that will perform sanding and polishing operations. this means that its minimum velocity needs to be close to 10 degrees per second. The first question is, will the given encoder suffice our requirements if we are updating our sensor measurements at 1 kilohertz? The second question, find the frequency at which this encoder would be able to measure our desired minimum joint velocity. And the third question, is there any problem for control if we use the frequency in question 2, in case we want to provide control signals to our motors at 250 hertz? So, of course, the data that we have in this problem, it's first the 13-bit resolution of the encoder, then the minimum velocity in which we want to operate, which is 10 degrees per second. And the first question tells us that we want to have an update frequency of 1 kilohertz. Then we need to find out the frequency. So of course, already from the question, you can tell that the first answer to this question, it's no. But we need to justify our answers. So that's what we're going to do in the next slides. Then we need to find the frequency at which we can satisfy the requirements. And finally, the last question, it's a bit of analysis. So we need to understand if there will be problems if we try to perform control at 250 hertz. So the next slide, this is the sensor that it's mentioned in the exercise. So let's start. So we saw that maybe I can change the color of this if this allows me to. Well, let's go with red. In any case, we're gonna also send you the resolutions of this, maybe written with better handwriting. So we know that the frequency, our sampling frequency, it's 1 kilohertz, so it's 1,000 hertz, and this gives us a sampling time of 0.001 seconds. Okay, so we're answering question 1. So we want to figure out if we can use this sensor to perform to measure velocity at 10 degrees per second. So to do that, we need to find out first the resolution of our sensor, which is going to be a full rotation of our sensor, which is 2 pi divided by our resolution. Remember that the resolution of so the resolution read as the number of bits that we use to measure. It's 13 bits. So let's put it here written 13-bit sensor. So to find out the number of bits that you have per resolution, you have 2 to the power of 13. Okay, so we divide 2 pi by 2 to the power of 13, and I already did this computation, which is 0.0007699 radians. Okay, and the minimum speed that we can measure, it's given by the resolution of our sensor, 0.0076699 radians, over our sampling rate, which is 0.001 seconds. So the minimum velocity that we can measure using this sensor is 0.76699 radians per second. Now, we said that we wanted our sensor to measure 10 degrees per second, which is equal to 0.17 radians per second. And of course, we can see already that the answer to the first question is the sensor, the sensor does not satisfy our specifications. Oop. Okay. Now, our second question is, okay, we can reduce the frequency at which we are measuring to match our specification if we want to use this specific sensor. So to do that, we check our minimum desired speed, which, as we said, is 0.17 radians per second, and our minimum desired sampling time is going to be the resolution of our sensor in terms of velocity, which is going to be, sorry, the resolution of our sensor, which is 0.766 99 divided by our desired minimum speed, and this is 0.0045 seconds. Now, it's not wrong. This is going to give you, so to get the frequency, you just need to do 1 over your desired thing, and this is going to give you like a strange number. So it's not bad to just say 0.005 and then 1 over 0.005. It's actually 200 hertz, right? Now remember that we said in the last, so this is the frequency that we need, let's say the approximate frequency that we need to measure a velocity using this sensor. So being able to measure a minimum velocity of 10 degrees per second. Now this is the answer to question 2. Now the answer to question 3, which is if we want to do control at 250 hertz, will this give us any problem? And of course, yes, because we want to do control at 250 hertz, but we're only providing, so this means that we want to basically change. So if our, let's call it FC, it's equal to our control frequency, it's 250 hertz. That means that our control, let's say we want to provide control signals every 0.004 seconds, which is the inverse of the control frequency. And we're only providing measurements every 0.005 seconds. So our controller is always going to be delayed. So yes, there are problems. Because sampling, well, let's put it, frequency is smaller than our control frequency. Yes, so the solution, let's say the more ideal solution, it's increasing the number of bits for the resolution of our sensor. So this is kind of the simple example that we're going to try to address in the exam related to the topic of sensors. Okay. Are there any questions on this? Pretty clear, right? So I'm gonna stop sharing, and then I'll go to the example on control. Yes. So 1 second. Okay. Give me 1 second. Okay. No. Okay, good. Okay. So let's read out the example of control. So in this kind of exercise, we're gonna, when we talk about control, we're talking about, for example, the kind of problems that the professor solved during the lab session, which was basically controlling an electric motor, design a controller for an electrical motor. So we can ask you to design a controller for velocity, which is the case of the example in which I'm doing. So this means that the transfer function is going to be different. Or we can ask you also to design a control for position. And then also one important thing is that we might ask different control laws that to the ones that I'm going to be showing here. So it's important for you to understand and read the kind of control laws that the alternatives that you may have to design the controller. So I'm going to read out the example, which is consider an electrical motor described by the following first order transfer function, neglecting the electrical time constant. So remember that if you neglect the dynamics of the inductor in the motor, then instead of having a second order transfer function, you have a first order transfer function. And this is the transfer function on velocity, on the angular velocity of the motor over the voltage. And this is 1 over 0.6 s plus 0.08. And the question is, design an ideal PID controller to achieve critically damped. So it is important to understand and keep in mind the different values of the damping coefficient that the type of responses need. So critically damped, over damped, etc. And response with us, and then to achieve a critically damped response with a settling time of 2 seconds. Okay, so let's start. So the first thing that we need to do is to, well, how I would proceed, it's to first draw the closed loop system block diagram. Okay, let me see if I can change the ink. Okay, so now it's black. So let's start from this side. So we have our reference velocity, and this will be a feedback controller. So there's always this that will subtract from the reference the actual value, and what's coming out, it's our error signal. And then we have our controller. Now remember that the equation for the PID controller, it's Kp. So remember, we're designing an ideal PID. Keep in mind that we might ask you to design the non-ideal case, but the procedure, it's very similar to this one. So this is the equation of our controller. Let's call this C. And then the output of our controller, it's U. And let's put our transfer function, which is our plant, 0.6 s plus 0.08. Let's call this G. And the output of our transfer function, it's our angular velocity. And then we send this back to our feedback. Okay, so now we need to work out our closed loop transfer function. Okay, so this means the transfer function from our reference to our angular velocity. So basically the transfer function of this. Okay, so the general way to find a closed loop transfer function of a feedback system is this expression, which is just multiplying the controller times g over 1 plus cg. And this is, so here I'm going to just work out the to put the common denominator on the controller. So I'm gonna do kps plus kds square plus ki over s times 1 over 0.6s plus 0.08. Okay, this 1 plus and the same that we have on top, kps plus kds square plus ki over s times, I'm going to start with the denominator, that way I won't have to extend the line. 1, okay. And then if we simplify the products of this, we can have so if we do the multiplications of the denominators of each of this expression, so we have s times, so we can do the common denominator of the denominator of the transfer function, which is going to be the same denominator as the one in the numerator of the transfer function, so this one. So we can actually cancel out this, and this, and then what we're going to have in the end is this kps plus kds square plus ki over, now if we're doing the common denominator, this is going to be on this side. So this is yes, so this is going to be 0.6 s square plus 0.08 s plus kps plus kds square plus ki. Okay, now we can rearrange a bit this expression, and the numerator we can keep the same, plus ki, but the denominator we can put together the coefficients of the square, linear, and independent term on the for the denominator, and this becomes 0.06 times kd s square plus 0.08 plus kp s plus, this is an s plus ki. Okay, so this is our closed loop transfer function. Okay, now for now we're gonna keep this on hold, And now we're gonna think about the response that we're asked for. So let's go back to our first slide, and they want us to, well, I designed this problem to have a damping coefficient of 1 and a settling time of 2. So we can design a second order response that can satisfy these requirements. Okay, so let's do this. So let's write down second order system response. Okay, so we were asked to have our system critically damped. So let's write it down. System needs to be critically damped, which means that our damping coefficient is going to be 1. Okay, so if we write down the general expression of a second order system, we have s squared times our damping coefficient times the natural frequency times s plus the square of the natural frequency. Okay, now in our case, this translates to s squared plus 2 times our natural frequency plus the square of the natural frequency, because we're setting our damping coefficient to be 1. Now, the requirement is that our settling time, it's 2 seconds. So how is settling time defined? So settling time here is the time that the system takes to be within 2%. So this requirement can change, but in general, I like to use 2%, but it can be 5% of the, and this will have an effect on the settling time, of course, of the steady state response, and not diverge. Okay, so in essence, what we're trying to say here is that the settling time, it's equal to 4 times the time constant of the system. So this is a basic concept in control. The idea of the time constant of the system, it's basically the rate at which the response moves towards the reference. And for now, you just need to know that it's 4 times the time constant at the settling time. But it's fairly easy to find it, because a time constant, it's defined as 1 over the damping coefficient times the natural frequency. So if we want our settling time to be 4 times the time constant, so we basically need to do 4 over our damping coefficient times our natural frequency. This one we already have. We said it was 1, and this one is a requirement of the system, which is 2 seconds. So we're only left to find the natural frequency. Okay, so this means that this leads to the fact that our natural frequency, it's equal to 2. Okay, so our desired second order system response boils down to s squared plus 4s plus 4. And we're just going to call it for now R of response of S. Okay? Okay, so we have the kind of response that we want for the specifications that we determined. So now what we need to do is to achieve the second order response, we want to, so I'm going to write it down here, to achieve second order response. So remember that what determines the response of a system, it's the denominator of the transfer function. So we're going to basically say that the denominator of our closed loop transfer function needs to be equal to the response of our system. Okay? And this boils down to what we worked out first, which was 0.6 plus kd s squared plus 0.08 plus kp times s plus ki equals, and this is equal to s squared plus 4s plus 4. Okay, and now we just solve for kp, kd, and ki, and we can just equate the coefficients, and this will give us the values of our gain. So we can say that 0.6 plus kd it's equal 1, 0.08 plus kp it's equal to 4, and ki it's equal to 4. And this turns out to be that kd it's equal to 0.4, kp it's equal to 3.92, and ki it's equal to 4. Okay, now let's put this in red. Oh. This is the design of our gains for this problem. Okay, any questions regarding this? Also fairly simple, I think. If there's something that's not clear in my handwriting or something, please let me know. So let's move on to the next exercise, which is on kinematics. And this is the one that it's, let's say, it's going to be the most time consuming in the exam, along with the one of dynamics. But you saw that the first two exercises are fairly simple, because they're just easy ways to demonstrate the solution of let's say to demonstrate the concepts of the course. So let me open it. Okay. One second. Okay. Okay, good. So let's start. So I'm gonna show you first the manipulator I don't know what happened. Okay. Okay. So this is the manipulator of the example. It's a PR robot, which is as a prismatic joint, then a rotational joint. So the first one is, so this is a prismatic joint moving in this direction, the positive direction. Then you have a rotational joint right here. Then you have another prismatic joint here moving in this direction, and then another rotational joint here. Okay, let me get rid of this. Okay, so let's go back to the description of the exercise. So consider the PR manipulator depicted in the next slide, and compute the following. So the first part and the most consuming one, it's computing the most time consuming one, it's computing the homogeneous transformation matrix from the base to the end effector frame, which is the transformation from 0 to the end effector. Then compute the geometric Jacobian, and then using the geometric Jacobian, compute the Cartesian space velocity, so the linear and angular parts of the end effector if joint 2 is rotating with an angular velocity of 1 radian per second. And the joint configuration is the two meters for the, so it's let's say it's a big robot. This is just for the numbers to be in the easy to compute, so that you don't spend much time doing computations on your calculators. So it's the first joint, it's 2 meters. The second, it's a 0 radians. The third one is at 1 meter, and then the final joint orientation, it's pi over 2, so 90 degrees. So here I'm giving you the side view of the manipulator. As I explained to you, it's PR, and the top view. So here, for example, on the side view, I'm showing you the manipulator at 0 degrees orientation, looking from the side. And here I'm showing you with a certain theta 2 angle. And this is the orientation. So this is looking from the top. So now that we have our, let's say, view of the manipulator, let's start solving the exercise. So in this slide, I'm keeping the drawings here so that we can use them as guidance. So let's start by finding the local homogeneous transformation matrices. So the first one that we need to find is, let me see if I can change the color of the pen to black. Okay, so the first one is from 0 to 1. And we see that this is a pure translation, because we're only moving in along this Z0 axis here. Remember, so we're gonna provide the location of the frames, just because it's very time consuming, and probably you won't have time to also solve yourself the orientation of the frames. So for now, I'm just providing these already in the exercise. So let's start. We know that it's a pure translation. So if it's a pure translation, we have identity in the rotational part. Then we already know that the 3 elements in the bottom are 0. So I'm already putting this. And then we are displacing along our Z axis here, the axis of motion of the joint. So this is Z0. So this is basically, now we have a joint, a link length at the beginning of A1. So what we're going to have is 0, 0, A1 plus the displacement of D1. Okay. And then this is our first homogeneous transformation matrix. Okay. Now, the second one, it's joint theta 2. And this one, it's a pure rotation, okay? And it's a pure rotation around the z-axis here. Here we have our z1 axis. So we do our pure rotation, and let's have it here 0, no, not 0, 1, 2, and this is a rotation around the z-axis. So we have cosine of theta 2 minus sine of theta 2, then sine of theta 2, cosine of theta 2, and then we have 0, 0, 1, 0, 0. We know that at the bottom we have all zeros, and then there's no translation, so this is 0, 0, 0, and our 1. That is our scaling factor. Then for the next translation, now we see that our axis of motion of the next joint is no longer aligned with neither with the base frame here, neither with the rotation axis. So actually, our axis of rotation is this Z3. So first, we need to do a rigid rotation around the y-axis. So consider that y here, it's pointing towards the slide. So not outside of the slide. So this is the y-axis pointing towards the slide, the y-axis of the set 2. So now we're going to perform a rigid rotation around that one of 90 degrees. So that is a positive direction because it's pointing towards the slide. Okay, so it's going to be a positive rotation of 90 degrees around the y-axis. Okay, so let's write it down here. But there's also the fact that this is a prismatic joint, so we're going to have to add also a translation that is going to be the translation due to the length of the link A2 plus the displacement of joint D3. Okay, so let's write it down here. So we're going to write a rigid rotation, and this rotation is going to be a rotation about y2 of 90 degrees plus a translation. Okay, so this is 2, 3, and then this becomes 0, 0. So this is a rigid rotation. Remember that this is going to be sine 2, then sorry, this is sine of theta, because it's a rigid rotation. This is the sine of 90 degrees. So this is 1, this element right here. Then this element, it's just the one that it's usually in the rotation around the y-axis, and then on this you have minus sine of 90, which becomes minus 1, and then you have 0, 0 here, and then we have our usual 3 zeros here. Okay, and then our translation is going to be along the x-axis of the predecessor. So it's going to be along this axis, which is the actually x2, that's moving along this direction. So that's going to be our translation. So here we have D3 plus A2 in the x-axis, 0, 0, 1. Okay, so we are in tree. Now I'm gonna use another slide to do the other two. So the next one, I'm gonna break it in two parts, just because it makes it easier to understand. So the first one, consider that now the axis of rotation. So now the next joint. So we already went through the first prismatic joint, the second rotational joint, and then we did the third, the prismatic joint, the second prismatic joint. Now we want to do the transformation to this rotational joint here. So now the Z axis, remember that the Z axis is always aligned with the axis of motion of the joint. So in this case, the axis of motion of the joint, it's pointing, is a Z pointing outside of the slide. Okay, so remember that Z3 was aligned, it's pointing towards the right. So what we need to do is basically take that Z3 vector and align it with the vector that it's pointing outside. And this is basically taking it a rotation back on let's say in the negative direction, because now x3 it's pointing downwards. Okay, so first we're going to do this rigid rotation of around the x3 axis of minus 90 degrees. Okay, so this is basically, I'm gonna call this 3T4 prime, and this is going to be a rotation now, because the rotation it's of 90 degrees around the x-axis. It becomes this. Remember that this is a minus sign, this is a cosine of 90, which becomes 0. And then, sorry, this is a sign, but because we are doing minus 90, this becomes a minus 1, this right here. And then this one becomes 0, 1, 0 here. We have our 3 zeros here. Okay, and then this becomes 0, 0, 1. Okay. Okay, so we have our rigid rotation. Now our axes are aligned. So now, because we are aligned with the Z axis, we just need to do a pure rotation around the Z axis of the joint. So this becomes sorry, let me write it down here. Actually, let me make a bit of space.
Excuse me.
Tell me.
Can you repeat why we do a rotation of minus 90 degrees?
Yes. So remember that Z3, it's aligned, it's pointing in this direction, right? And then Z4 is the axis of rotation pointing outside of the of this light. So if you look at the top view, Z4, it's pointing in this direction. So this is pointing outside of this light. So Z needs to be rotated around the x-axis here to basically align Z3 with Z4, which is pointing outside of this light. So imagine.
So Octavio, isn't a 90 degrees rotation positive 90 degree?
No, because since the axis Z is pointing outside of the slide, the positive rotation, it's actually in the. So if you do the Z, a positive rotation, it's like this. Okay. So if you do like this, so if you do the rotation around X, if you do this rotation here, it's a negative rotation actually, because how can I say this? this, yeah,
So it's pointing inside the slide if you do a negative one, I think.
Give me 1 second because I did this by myself, and I checked it in MATLAB actually, or maybe I wrote it wrong here. Let me just check real quick. Okay, so oh yes, you're right. It's a positive rotation. This matrix, it's actually a positive rotation, I think. Yes, it is a positive rotation. So it's a positive rotation about the x-axis. You're right. It's just that I wrote it. I had a minus here that it's not supposed to be there. So yes, it is a positive rotation. Okay, sorry about that.
Okay, if you can, in the drawing, correct the. I mean, it's not. It's just bad written. It looks like a 1, but it's a 4, right?
Which one?
Z4. Z4.
You mean this one?
In the top view, the Z4 looks like a 1.
This one.
And also
yes.
the theta 4.
Yes, I will correct it in the one that I mean, I can do it now. I cannot erase here. So
yeah, but right on top of it, just to avoid the confusion, then we make it a little bit more clear in the.
Yeah, this is A4. Okay, 4, 4. Okay. Okay, so this is set 4 theta 4. Then since we already did the rotation in around that axis, then we have a pure. Well, by the way, was this clear? This answer your question?
Yes, thank you.
Okay. So we have the pure rotation here. Okay. And then here we have now actually 3T4, and then it's a pure rotation about the z axis. So this becomes C4. So cosine of theta 4 minus sine of theta 4, 0, 0, S4, C4, 0, 0, 0, 0, 0, no, 1, 0, 0, 0, 0, 1. And this is our rotation about the z-axis corresponding to the homogeneous transformation matrix from frame 3 to frame 4. Okay, so now we want the transformation to the end effector. And this is basically it's going to be a rigid rotation and a rigid translation. So the rigid rotation is to match our z-axis that it's pointing outside of the end effector here, set EE. So our set, it's now in set 4, it's pointing outside of the slide, and now we want to rotate it to point in this direction. So now, in fact, this is a negative rotation because if we rotate set in the same, if we align set 4 with the set end effector, then the rotation is negative because let's say the thumb, it's pointing in the direction towards in this direction if we rotate negatively. So this is, if we align them, then the rotation is going to be in that direction. Okay. This is the pure rotation, and then there's a rigid translation, which is just basically the distance A3. Okay. So I'm going to write it here. Rigid rotation of, and this rigid rotation corresponds to a rigid rotation about the x4 axis of minus 90 degrees and plus a rigid translation. Okay, and this becomes 1, 0, 0, 0, 0. Yes, and this makes sense with respect to the previous one because this is a minus sign of minus 90. It becomes 1, and then this is 0 minus 1, 0. Okay, 0, 0, 0. And then we have our translation along the y4 axis in this direction. Okay, and this is 0, 8, 3, 0, 1. Okay, good. So we have our local homogeneous transformation matrices. Now I write them down all here. Yeah, actually I had it correctly here. So now let's compute the global homogeneous transformation matrices. So to do that, so the first one, it's easy. It's just this one. I'm just copying the same one as we had before. 0, 0, d1 plus a1, 0, 0, 0, 1. Okay, then 0 t2, it's going to be 0 t1 times t2, and this is just basically performing the matrix multiplications. I already did this computation, and just for the sake of time, I'm just going to put it down here. C2 S2 0 0 S2 C2 0 0, and then 0 0 1 D1 plus A1 0 0 0 1. Okay, now we do the same for 0 to 3, and this is basically 0 2 times 2 t3, and this becomes, again, we just perform the matrix multiplications as 2 c2, and then this is the 3 plus a2 times cosine 2, then this is 0 c2 s2 d3 plus a2 sine 2, then minus 1 0 0 d1 plus a1, then 0 0 0 1. Okay. Okay, I'm running a bit out of space. Let's see if I think I have the last one. Well, let's see if I manage to fit it in this side. So I'm going to try to do it like this. So we all know that 0t4, it's just the multiplication of 0t3. Well, let's do it here. 0 t3 times 3t4 prime times well, I should have called the other one, actually the name that I gave it just to make the inner sub-indices match. It's like this, okay? And this is here, cosine 3. No, sorry. Cosine 2 times sine 4, then sine 2 times sine 4 minus cosine 4, 0. Then here, cosine 2, cosine 4, sine 2, c4, sine 4, 0. Then sine 2 minus cosine 2, 0, 0. And then d3 plus 2 times cosine 2, then d3 plus 2 times sine 2, a1 plus d1, 1. And then this is our homogeneous transformation matrix 2, 4. And then for the final one, to the end effector, we have 0 t e it's equal to 0 t4 for end effector, and then this is cosine 2 sine 4 sine 2 sine 4 minus cosine 4, 0, minus sine 2 cosine 2, 0, cosine 2 cosine 4 sine 2 cosine 4 sine 4, 0, 0. And then d3 plus a2 times cosine 2 plus a3 cosine 2 cosine 4, then d3 plus a2 sine 2 plus a3 sine 2 cosine 4, then a1 plus a3 sine 4. And this is, let's put a red square around it. This is our answer to question 1. Okay, good. So this is the most time-consuming part. So now the next thing that we need to do, sorry, I didn't delete this. Let me go to the next slide. Okay, so let's compute the geometric Jacobian, which is the second question. So remember that, let me just put back the black. So our geometric Jacobian, it's made of the number of, so it has a number of columns equal to the number of joint space variables that we have. So let's start. So our first column is going to be corresponding to a prismatic joint. So if you remember the expression of the columns of the Jacobian for a prismatic joint, it's basically the direction of the set vector of the prismatic joint and 0 in the bottom part and for the rotational part. For the rotation part, for a rotational part, which is our second joint, we have the cross product of set 2 cross the position vector from the base to the end effector minus the position vector to the frame corresponding to the joints. Yes, this is 2 over set 2. Okay, then another prismatic joint, set 3, 0, and then finally, finally a rotational joint, which is set 4 cross 0 PE minus 0 P4. Okay, over set 4. Okay, so the steps that we're going to follow to compute the Jacobian, it's going to be like this. One, we first compute the set I vectors, then we find the position vectors using our global homogeneous transformation matrix. That's why we went through all of that trouble of doing all of them at the same time. And then, oh, sorry. Let me go back. Okay. Then 3, we compute the cross products. Okay, so these are the 3 steps that we're going to follow. So let's start by computing the set I vectors. So I'm going to write it down here. Actually, well, so the first one, it's fairly easy because it's the axis of motion of the of joint 1, which is moving in this direction, which is aligned with the base frame. So set 1, it's equal to 0, 0, 1. Okay, then set 2 is actually easy as well. Let me write it, because set 1 and set 2 are aligned here. Whoop. Here. So the axis of rotation, it's actually this one here. So set 2, it's equal to set 1 and is 0, 0, 1. Okay. Then for set 3, what we're going to do, it's also fairly simple, because we know that all of the vectors are going to be 0, 0, 1, but we need to transform them to be with respect to the world frame. But we already computed how our homogeneous transformation matrices. So what we do is, actually, we get from our homogeneous transformation matrix, we get our rotation matrix. So this comes from 0 T3, and then we just multiply the vector set 1, because it's just basically transforming the z axis into the rotation of rotating it with respect to the world. And then what turns out of this multiplication is just set cosine of 2, sine of 2, 0. Remember that one easy way to check if this is correct is that the result of this needs to be a unit vector, and this is in fact a unit vector. So then here set 4 becomes we'll do the same. We get the rotation matrix, then we multiply set 1, and then this comes from the homogeneous transformation matrix. And why is this doing this? Okay. And then I think because the temperature of the tablet is getting really hot, it's detecting every small change in temperature as as me changing the slide. Anyhow, so we have this equal to sine 2 minus cosine 2, 0. And then we have all of our set vectors, okay? Now that we have all of them, we now go to our second step, which is finding our 0 pi from 0 ti, okay? And here I'm just going to copy directly from the matrices. So we have 0 p1. Remember that in our homogeneous transformation matrix, you have the rotational part, the position part, 0 and 1. So what we're looking for is this, okay, in this part. So this is what I'm getting here. I'm going to make it here. So 0 p1 is 0, 0 d1 plus a1. Then 0 p2, it's equal to, actually, in our homogeneous transformation matrix, these are the same. 0, 0 d1 plus a1. Then 0 p3, it's equal to d3 plus a2 times cosine 2, d3 plus a2 times sine 2, d1 plus a1. Then 0 p4, it's actually equal to 0 p3. So this is basically d3 plus a2 times cosine 2. And then d3 plus a2 sine 2, d1 plus a1. And then finally, we have 0 p to our end effector, which is d3 plus a2 times cosine 2 plus a3 times cosine 2 cosine 4. Then we have d3 plus a2 sine 2 plus a3 sine 2 cosine 4. Then a1 plus d1 plus a3 sine 4. Okay. Actually, the only ones that we actually needed, if this allows me to continue, were the ones related to the rotation matrix, which were sorry, to the rotational joints, which were 0 p4. Of course, we needed the end effector one, so we only needed these three because we're only going to use them in the cross product. But in any case, I'm putting all of them here. So the third part is to compute the cross products. Okay, so this is basically computing Z2 cross 0 p end effector minus 0 p2, and this is actually equal to, remember, our skew symmetric matrix, that we use to do cross products, because this is easier to do by hand and then performing the actual cross product. So you can do it like this in the exam, and this becomes 0p2. Okay, so remember that set 2, it's just 0, 0, 1. So in our skew symmetric operator, this becomes 0. Then this is -1. Remember that this is so if we call this let's call this, oof. So let's do it like this. Oh my god. Well, let's call this x, and this is x1, x2, x3. So this is in the skew symmetric operator. Let's put it, I'm going to put it right here. So if we have a vector x composed of x1, x2, and x3, the skew symmetric matrix of this one is 0, minus x3, x2, minus x1, and then x3 minus x2, x1, 0, 0 here. Okay, so this is basically what I'm doing here. So this is 0, 1, 0, 0, 0, 0, 0 times this difference here, which turns out to be d3 plus a2. I'm running out of space, so I'm gonna put it below. So this is equal to 0, minus 1, 0, 1, 0, 0, 0, 0, 0 times d3 plus a2 times cosine 2 plus a3 cosine 2 cosine 4, then d3 plus a2 sine 2 plus a3 sine 2 cosine 4, then a3 sine 4. Okay, and in the end, the result of this multiplication is minus d3 plus a2 times sine 2 minus a3 cosine 2 cosine 4, then d3 plus a2 cosine 2 plus, remember it's just this times this, this times this, this times this. So this times the vector, this times this, so this becomes a3 sine 2 cosine 4, and then 0 at the bottom. Okay, so we have our first cross product. Then let's go for our second cross product. I'm just going to, I think I don't have it written down, so I'm just going to go fast through it. So I'm going to write directly this cross minus 0p4 equals, and now the skew symmetric matrix of set 4, remember that set 4 was a minus c2. Yes, let me just check this just to verify that I'm not saying something weird. Sorry, so this was sine 2 minus cosine 2, 0. Okay, so our skew symmetric matrix becomes 0, 0, minus cosine 2, minus sine 2, and then this is 0, 0, cosine 2, sine 2, 0, times A3 cosine 2 cosine 4, A3 cosine 2 cosine 4, A3 sine 4. Okay, then the product of this, if we just do the matrix multiplication, we get minus A3 cosine minus A3 cosine 2 sine 4 minus A3 sine 2 sine 4, and then A3 cosine 2 squared cosine 4 plus A3 sine 2 squared cosine 4. Okay, so
Excuse me,
yes,
maybe there is also a minus d1 in the x
and next in the
x coordinate of and the factor p 0 pe.
let me check,
Because 0 p4 is a1 plus d1.
yes, but if you look, so let's do it. We have it here, so 0 PEE is equal to, so we're just talking about the last component, right? So you have A1 plus D1.
Okay, I didn't count d1.
Yeah, so you
Okay.
have A1 plus D1, and then you have the other one. In the before you also have D1 plus A1.
Okay.
Yeah.
Sorry.
No problem. Okay, so okay, we have our cross products. So basically, it's just replacing this into our Jacobian, and this is the answer to our second question, which is the computation of the geometric Jacobian. So now we go to the last part of our question, which is compute the Cartesian space velocities for an angular velocity of joint 2 of 1 radian per second at this joint configuration. Okay, so let's start by writing our vector of nth vector velocities. Which is equal to our Jacobian times our joint velocities. Okay, and this is equal to yeah, I'm gonna write down the Jacobian. So 0, 0, 0, then minus, so it's 6 already. Well, there's enough time. D3 plus A2 times sine 2 minus A3 sine 2 cosine 4, then D3 plus A2 times cosine 2 minus A3 cosine 2 cosine 4, then 0, then 0, 0, 1, then we have cosine 2 sine 2 0, 0, 0, 0, and then minus a 3 cosine 2 sine 4 minus a 3 sine 2 sine 4, then a 3 cosine 2 square cosine 4 plus a 3 sine 2 4 cosine 4, and then sine 2 minus cosine 2 0, and this goes all multiplied by 0 1 0 0. Okay, so if we perform this multiplications, I'm missing a bracket here, we end up with minus d3 plus a2 sine 2 minus a3 sine 2 cosine 4, then d3 plus a2 cosine 2 minus, no, plus a3 cosine 2 cosine 4, 0 0 0 1. Okay, times, no, not times, so this is our metric multiplication. So now this is equal to, so now we going to replace the values of our joint variables in our vector. So d3, well, let's start with the sign. So in this way, with our joint variables, so in this way we can get rid of all the signs. So our joint 2 is 0, so here we have sine of 2, so these two terms, they become 0. Then you have cosine, this becomes 1, this becomes 1, and then you have cosine of 4 here is pi over 2, so this is also becoming 0, and then you end up just with this term and this term, and the 3 is 1, the a2 is 1, so in the end you end up with your 0 2 0 0 0 1. Okay, and this is our vector of, let's put a red color to it. Our joint velocities. Now let's check if this makes sense. So this is the joint configuration that that was asked for in the exercise, and we're saying that theta 2 is rotating at an angular velocity of 1 radian per second. Okay, so the velocity that we got in the end was 0 2 0 0 0 1. Okay, so this means that the velocity in the y direction is 2 meters per second. Okay, so now let's think about this. If this theta is 0, it means that we know that the linear velocity, it's equal to r cross omega. Okay, and in our case this is just the scalars, so our r, it's basically a2 plus plus the 3, which is 1, this becomes 2, and our angular velocity is 1. So actually, because this is at 90 degrees, we get a full component going inside of the slide, which is the positive direction of the y-axis and the base, that is moving towards the slide at 2 meters per second. And for the angular velocity, since this is the only joint that is moving, which is moving, theta 2 dot is moving with 1 radian per second, so this is the 2 that corresponds to this, and this is the, and it's rotating around the z axis of our of our manipulator. So in the end, this answer makes sense. Okay. So this is the exercise on kinematics. Are there any questions regarding this exercise? Okay. Yeah, this is going to be one of the most time consuming ones in the exam, just because you need to compute the homogeneous transformation matrices and do some matrix multiplications, but the numbers are, I mean, you saw that the numbers here are simple, like they're chosen to make the computation easy. Okay. Okay, so let's go to the last exercise that I prepared myself, which is in joint space control.
Octavio, do we want to do a 10 minutes break?
Yes,
Or
yes, you're right. Let's do a break. Let's do a 10-minute break. Let's reconvene at 17, 6,
17. Okay.
Yeah. Okay. Okay. I think we didn't record that last exercise that I did.
Yeah, sorry. Yeah, sorry.
No problem. It's fine.
Yeah. So as I said, the next exercise is to solve the problem of statics, where you want to find the balancing torques to create an indexator force effects of in the plane, because we are living in the plane we have only xy directions. So square root of 2 is are the coordinate xy of our end effector force, and we want to create this force with a robot. It is a 3 degrees of freedom robot, and it's a PRR robot, so prismatic joint followed by 2 rotational joints. The robot is in a specific configuration, which we will see is we can set any number for the first joint, and the second number 3/4 of pi for the second joint, minus pi for the third joint. So to solve this exercise, you remember we want to apply the principal Winter work and find the relationship between torques and effector forces. And so we first compute the forward kinematics for this robot, which is f of q as 2 components, because we are living in a plane, we don't care about the z one. And the first one is then the effector position is here, so we have a contribution with respect to the frame, base frame of q1 plus dc1, and we arrive to here. Then we apply this other part, which is L2 cosine of 2 plus the third link contribution to the kinematics, which is L3 cosine of 2 3, which is the sum of joint Q2 and Q3. Then second component on the y component, the first one doesn't have any contribution, and we have only contribution due to the second joint is with a sine, this segment, and then this other segment, which is the sum of this L2 times L3, sorry, times the sine of 2 and 3. Then if we compute the derivative of this partial derivative, we get the Jacobian. With respect to the joint variable, and we in essence differentiate the first term, the first coordinate expression, symbolic expression for the variable q1, and we see that there is a 1 here. This is 0, 0, 0, because q1 is not there. Then we differentiate with respect to q2, and we get L2 sine of 2 with a minus, and 2 is also here, and we have again a minus L3 sine of 2, 3, because the minus sine is the derivative of cosine. Then the third, with respect to the third one, we have only this term which contains Q3, and we have L3 minus sine of 2, 3. Then for the second term on the second coordinate, the y coordinate one, we in essence have 0 with respect to 1. It doesn't exist into here. And then you have L2 cosine of 2 plus L3 cosine of 2. And the third one is, sorry, this is 2, 3. And the third one is L3 cosine of 2, 3. Now we using this Jacobian, we can notice that is singular, so it gets for example, in this case, a rows of zeros and loses rank. In case of sorry, this is 2, 3. In cases where both cosine of 2 and cosine of 2, 3 are becoming 0. And this means that this happens whenever this joint is on this line and this other joint, because this angle should be 0, is also on this line. So both third and second link are lying on a line of the first link. But we ask to map the forces in this configuration. So let's evaluate. Let's first draw this configuration. Let's evaluate the Jacobian at that configuration. And so in Q, any 3, 4, 5 minus pi, you have in essence the first joint. 3, 4 pi is under 35 degrees, right? So it's a little bit beyond, this is 45 degrees. And minus pi is just, if this is 0, it's completely folded. Note that, sorry, I didn't say, L2 and L3 have unitary length. So then the factor is exactly at this point. So the angle theta 2, 3 that we are interested to compute the Jacobian is 3/4 pi minus pi is in essence minus pi 4, which is exactly this angle with respect to horizontal. So it's the angle with respect to the link one axis. So the Jacobian in this configuration becomes we have an independency from the Q1 variable. That's why we put arbitrary, because you will see in the Jacobian there is no Q1 variable. So we have 1, and we have in essence L2 sine of 2 plus L3 sine of 2, 3. And because theta 2, 3 is minus pi 4, and theta 2 is pi 4, sorry, is 3/4 pi 4. We are talking about, in essence, this angle and this angle. You see that they both have, this is negative sine and negative cosine, positive cosine, and this is positive sine and negative cosine. And both of them have this value because it's a 45 degrees cosine and sine, and they both have a square root of 2 divided by 2 value. So in essence, this term in the middle, they become 0 because they have opposite signs, values of the signs, so it's becoming 0 and cancel each other. And the third one is just the minus, the third element was minus L3 sine of 2 3, and for this angle the sign is minus square root of 2 divided by 2, so minus that becomes square root of 2 divided by 2. Then we have a 0 here. Again, we have a cancellation of the cosines that have different signs, so this also becomes 0. And then you have L3 cosine of 2 3, and cosine of 2 3 again is positive and is square root of 2 over 2. Now, if you want to compute the torque relative to that external force, we apply the static principle with the works, and we get Jacobian transpose Fx, and this is in essence 1 0 square root of 2 divided by 2 and 0 0 square root of 2 divided by 2 times our external force Fx, and this becomes in essence, this goes here, this goes here, so we get a minus, let's put the minus outside, square root of 2 and then 0, and these two, they both become 1 plus 1, so 2. Okay. Everything is clear? So this was quite a simple exercise. Let's move on to the dynamic one, such that we have time to go through the questions, to the quiz, and multiple open questions for the exam. So here is the robot.
Yeah, you're not sharing your screen.
Yeah, I need to share the screen. Okay. Okay. Is the dual of the one we saw at the lecture. It's a RP robot. We had the lecture we saw, remember in the lecture about the Lagrange approach, we saw the PR robot. And actually, we will see that the equations are much worse. The exercise that we put in the exam will be less involved. This is just an example. And this is because the rotational joints, they mess up things because of the cosine and sine. And so we have the first link, which is as a mass of m1 and a tensor, a moment of inertia around the z-axis, which is coming out from the screen, from the slide, of J1. So this is a scalar. And a second link has a mass of J2, mass of M2, and J2 is the moment of inertia about the center of mass of link 2. So if we want to compute the moment of inertia, the tensor of inertia, we will see that we don't care about the component out of except the z component of the tensor of inertia, because we are involving rotation only around the z-axis. So this this is a planar robot. It's moving in a plane, and therefore we will see that the component along the z-axis are always 0. So to compute the kinetic energy, let's try to use the Koenig theorem, the second Koenig theorem, that allows us to write the kinetic energy for the two links. So the total kinetic energy, the kinetic energy of the first and the second link. And for the first link, using Koenig theorem, we get T1 1/2 M1 VC1. For the we can split this way using Koenig theorem the linear kinetic energy, the kinetic energy due to the linear motion, to the translational motion, from the kinetic energy to the due to the rotational motion. And this is the velocity of the center of mass of link 1 plus 1/2 omega 1 angular velocity of link 1 I1 omega 1. Okay, now the to compute the velocity of the center of mass of link 1, we need the position of the center of mass of link 1, and we see that we have the d1, which is the distance from the center of mass to the joint axis, and we need to multiply by the cosine of q1 for the x component. Note that here x and y component are flipped. This is made on purpose to keep your attention high. And this is the y component, and it's 0. And the velocity, the linear velocity of a central mass of link 1 is just the time derivative of BC1. We have d1 s1 times the derivative of q1 dot, and d1 we have derivative of the sine, which is cosine, times again the derivative of q1. Sorry, this is 1, and we have 0 here. And what is the omega 1? So the angular velocity, in this case, the rotation is only around the z-axis, so we expect to have an angular velocity of q1 dot magnitude around the z-axis due to the joint 1, which is a rotational joint. Then if we put everything together to compute T1, the kinetic energy, we have T1, we are going to do the square, so we square the first component, then we square the second component, and we sum so all of that. And we need to multiply by the mass, plus we have 1/2 the rotational part, which, because of omega is made this way, will extract from the I1 matrix only the ZZ element, because this is 0, 0, non-zero, non-zero. If we do the multiplication, we see this. So in essence, we get a scalar q1 dot squared is a quadratic form. If you pay attention, these two are summing up to 1, and in essence we have for free what the application of the parallel axis theorem would have given us if we want to compute the inertia not with respect to the center of mass, but with respect to the rotating axis, which is here. So This J1 is just a rotation around the center of mass. If we want to apply the parallel inertia theorem and define the inertia about another axis not passing through the center of mass, we need to add this other term, which is just a point mass rotating at a distance d1 from the inertia of a rotating mass, point mass rotating around the z axis. Now let's do the same thing for a joint link. Sorry, P2. Sorry, we need to compute the center of mass of link 2. And if you remember a previous picture, we have that the center of mass of link 2, and I will quickly draw this here. This is Q1. This is L1, and this is. Remember that I defined the. If you saw the previous picture, I defined the Q2 as the location of the center of mass, just for simplicity. So this is Q2 in essence. And so to compute this, we need to the x coordinate. We take L1 cosine of Q1, and we need to this is x coordinate, y coordinate, and we see that we need to subtract what Q2. So this is Q1. Sorry, this is the opposite of Q1. So this is the same angle. Therefore, this is 90 degrees. This will be Q1. So Q2, we need to subtract Q2 sine of Q1, which is this segment. For the y coordinate, instead we sum them up. So that's L1 sine of 1 plus Q2 Q2, which is this segment, cosine of Q1, this segment. So this plus this. And the third one is 0. Again, if we compute the velocity as time derivative of position of central mass of link 2, we get something more involved. L1 S1 Q1 dot derivative of this minus S1 Q2 dot. Both of this depends from time, so we have also the other one, which is minus S1 derivative of the second, sorry, cosine of 1 derivative of S1 times Q2 times the derivative of Q1 dot. And that's the y is the derivative of this L1 cosine of 1 plus C1 Q2 dot plus, which is a minus because we need to differentiate this S1 Q2 Q1 dot. The omega of the second link, does anybody has an idea of how much is that? How is can be written? Remember, the omega is the variation of the orientation of the frame attached to the second link. And because the second link, even if it is a prismatic joint, is driven by the first one, which is the rotational joint, it will rotate with the same angular velocity. So its frame will change its orientation with the same rate. Therefore, the omega will be the same and is q1 dot as a q1 dot vector pointing up in that direction of the first joint axis with a magnitude of q1 dot. Now if we compute kinetic energy for this link, we get 1/2. Now we need to do the square of this plus the square of this, because this is a Euclidean norm, and we can simplify this by defining two. We collect in essence this term. Sorry, I will rewrite VC2 to make it simpler, and this is minus L1 S1 plus Q2 C1 times Q1 dot minus S1 Q2 dot. So I collected in essence Q1 and I call this A. And then for the y coordinate, I collect Q1 again minus Q2 S1 and I call this B. And with this in mind, we can compute the square of this Q1 dot, so square of this, the first term, the square of the second term, and the double product of the two, which because of the same minus sign will be positive. A S1 Q1 dot Q2 dot plus the square of the second component, which would be B squared Q1 dot squared plus C1 squared Q2 dot squared plus the double product of the two of these two, which is B C1 Q1 dot Q2 dot everything times M2 plus the rotational part, which will be, as I said, extracting the Z component of the tensor of inertia, which is J2, because we said it's just a scalar part. Okay. Now we can do some simplifications. We see that this term and this term becomes Q2 dot squared, and we want to see that these two terms, they are also multiplying Q1 squared dot, and these other two are multiplying both Q1 dot Q2 dot. So let's see how it goes. If we collect A squared plus B squared, we have, sorry, let's do A squared is, let's write like this, L1 S1 plus Q2 L1 square Q1 square, sorry, L1 squared S1 squared plus Q2 squared C1 squared plus the double product. So this is just A squared and B squared is L1 squared C1 squared plus q2 squared s1 squared plus the double product, which is a minus, sorry, because this is a minus here, q2 l1 s1 c1. And we see here that there's quite some simplifications. And so if we do a squared plus b squared, we have this goes to 1, this goes to 1, and also these, and these are the same, can be collected. So in essence, we have L1 squared plus Q2 squared. And sorry, these are the same things that can be cancelled each other. While if we want to do, if we compute the other thing that we need, which is this, and a S1 and B C1, we see that we get L1 S1 squared plus Q2 C1 S1, and B1 C1 squared is L1 C1 squared minus Q2 C1 S1. So we see that if we sum this by this, these two, again, this term goes away, and we have that this one sum ups to 1. So in essence, a S1 plus B C1 is L1. So we can collect this and simplify a lot the equations for T2. And we get, in essence, the 1/2 M2 L1 squared Q plus Q2 squared times Q1 squared dot, the Q1 dot squared, plus the term that was here, that is becoming 1. So 1/2 M2 Q2 dot squared plus the term due to this, which is what was, sorry, yeah, L1, yeah, L1. So 1/2 to L1 Q1 dot Q2 dot, and then we have the angular term, which is again this. So if we put everything together, in essence, we get 1/2. This is the T1 part. And this is the T2 part. We collect again L1 squared plus Q2 squared plus 1/2 M2 Q2 dot squared plus M, this, sorry, this was M2 here, L1 Q1 dot Q2 dot, and finally the rotational part. And if we look at the, let's use different colors. So if we look at the, you remember you can express the kinetic energy as a quadratic form and extract the terms of the inertia matrix directly inspecting this. So this is whatever is computing, multiplying Q1 dot squared is the M11 squared, M1 term. Whatever is multiplying instead Q2 dot square is the M22 term, and the coupled term M12, which is because the symmetric is equal to M21, are both summed up in here. Therefore, the mass matrix, the inertia matrix is D1 squared M1 plus M2 L1 squared plus Q2 squared plus J1 plus J2. Then we have the coupling term M2L1, M2L1. You remember this is because they don't have an half, they already as is. Then you have the constant term due to Q2 dot squared. And notice that the this term is constant because the last link of the manipulator is not dependent on the configuration. And we also have that we have no dependency on the Q1 variable because the Q1 is just really will vary depending on the choice of the configuration of sorry, the reference system that we choose, and not so it will not affect the inertia. The inertia should not be changing because of the choice of the reference system, because it's an intrinsic property of the robot. Then for the centrifugal Coriolis, we get that this is the bidimensional vector because you have a 2 degrees of freedom robot, first coordinate, second coordinate, and each coordinate can be computed thanks to the Christoffel symbols expression, which is this one with a little bar here this way. And the Christoffel symbol, you remember, is 1/2 the derivative of the kth column of the inertia matrix with respect to the joint vectors, vector of joint variables, plus its transpose minus the derivative of the inertia matrix with respect to the kth component of a joint vector. So this is a scalar, this is a vector, and this is a scalar. And if you look at the first Christoffel symbol, we get 1/2. We look at the first column of the inertia matrix, which is this one, and we see that the derivative, we first differentiate the first element, which is this one, with respect to Q1, and we see that we said that there is no dependency on Q1, so we have 0, and then we have we differentiate with respect to Q2, and we see that there is a dependency on Q2 in here, so we have 2 Q2 M2. Then The second term are constant, so both their derivative with respect to Q1 and Q2 are 0. The transpose is just the transpose of this. So this term goes on the bottom left. Minus the derivative of the matrix. So each term of the entry of the matrix we differentiate with respect to what? To Q1, because it is the first term. And we say that 0 for the first term, and also the other ones that are constant are 0. So this is the first Christoffel symbol, which is just a diagonal with zeros on a matrix with zeros on the diagonal and of diagonal term this way. Okay. Then for the second one, we repeat the same procedure. And we get now we do the differentiation of the second column with respect to Q2, but the second column is constant. So its derivative with respect to Q2 and Q1 is 0. Sorry, yeah. So it's a matrix of all zeros. The transpose is again zeros. The only thing which is non-zero is whenever you differentiate a matrix for Q2. What is the term? These three are both zeros because they are constant. So the only one is this one, and the differentiation with respect to Q2 of this term, this entry is 2 M2 Q2, and the other ones are zeros. So we get, in essence, again, this simplifies here, and we get M2 Q2 0 0 0. Then if we multiply left and right for the Q dot vector, we get the remember this is Ci is Q dot. Okay, we call it K. And so we get, in essence, because it's a quadratic form, we get M2 Q2 Q1 dot squared. No, sorry. Let's see, how much was the first one? So the first one has only the off diagonal term. So they will be multiplied by M2 Q2 by the Q1 dot Q2 dot term. While the this one is the diagonal one, is relative to the variable Q1 dot, so will be minus M2 Q2 Q1 dot square. Okay. Then for the potential energy, because we are this robot, it's on a vertical plane. You remember we said it at the beginning. I'm not sure, but maybe I think I said that. The potential energy is just the sum of the contribution to the potential energy due to the two links. So we look at the center of inertia position of the two links, and we project that position for the gravity vector and take the minus sign after multiplying by the mass. And if we look at this, now there is a trick here. You need to be very careful, because if you look at the way we define the frame, reference frame, I did it on purpose, now is pointing down. So the G vector has not the Z component with the G value, 9.81 value, but the X component. So you get minus G, it's 9.81, along the X component, 0 and 0. This is a row vector because you do the transpose, and we get the expression for P1 which is, we copy here, T1 S1 0 minus M2 again minus G 0 0, and we have L1 C1 minus Q2 S1 L1 S1 minus plus Q2 C1 and 0, and this becomes M1 G D1. We take only this that are non-zero, C1 plus M2 G. Again, we take only the first one, L1 at C1 minus Q2 S1. And if we want to compute the gravity vector, the components, component-wise, you differentiate this with respect to the joint position vector. And we get the first component, we differentiate with respect to Q1. We see that the only term is affecting this are this. So we have M1, the cosine becomes minus sign. So we have a minus sign here at the beginning, and we have D1 sine of 1 minus M2G, again, same thing. And minus M2G Q, this is a plus C1, no, minus. Then the second component, we differentiate about with respect to Q2, and we get only this term, so M2G S1, the minus before. Okay, then we put everything together and we get the dynamic model of the robot. You see the gravity term only depends on the position. We have a torques here. And now we want to assume that we are in the horizontal plane. And we want to drive joint 2 in a way to compensate couplings from joint 1 motion. And the motion you want to follow for joint 1 is a sinusoidal motion. This is the desired trajectory, and is sine of omega t with an amplitude of 2. So if we look at the derivative of this, to be consistent, we should do 2 omega cosine of omega t. And the derivative, again, for the acceleration will provide us minus 2 omega squared sine of omega t. And for the second joint, we want to be fixed in a specific configuration, which is this one, 1/2. This means that the desired velocity is 0 because it's constant, derivative of a constant, and also the acceleration. Now to get these effects, we cancel the gravity term because we are in the horizontal plane. We consider only the inertial plane. We put the model in matrix form. E1 M1 plus M2 L1 squared plus Q2 squared plus J1 plus J2 M2L1, M2, 2L1. This is inertia matrix multiplied by the acceleration, the vector of joint acceleration, plus the Coriolis term, which remains M2 Q2 Q1 dot squared, and this is driven by the vector of joint coordinate. Sorry, this is wrong. This was y. They are generalized forces, and specifically the first joint you remember is like a rotational joint, but the second one is a prismatic joint. So you have a force, a torque, and a force. In a force, and if you look at the we replace in essence the we want to compute the forces that the second joint should use to compensate to compensate for the motion of the first one. In essence, we look at the second equation and we replace the desired acceleration that we computed before, which is q dot desired plus, we said that the desired acceleration for joint 2 is 0, so we don't consider that, and we still have the m2 q dot q2 desired q1 dot desired squared. Okay, and then this is equal to the force we want to compute, F2. So if we replace explicitly, we have M2, L2, L1 minus 2 omega squared sine of omega t minus M2 1/2. The derivative was the cosine one. So with 2 omega cosine minus 2 to the power of 2 omega squared cosine of squared omega t. This goes away, and in essence we get this expression. Okay, do you have any question about this? Okay, now I would like to quickly go through some possible questions that we can do in addition to the exercises. I share the screen of the other computer. Okay, you see that?
Yes, we see the screen.
Yes.
Okay, so there are some questions, for example, example question for sensors. We have two kinds of questions, quiz questions with true false reply. And for example, these are the noise in a signal contains useful information for diagnostics. This is false because, for example, is the disturbance in a signal that it contains useful information for diagnostics. The noise is just not useful. The accuracy of measurement system can be improved with a calibration procedure. For example, this is true. The resolution of a sensor is the smallest increment that a sensor can detect. Again, this is true. And you see here a tricky question where you say a random error can be compensated by a calibration procedure. And this is not true because it's systematic error that you can compensate with a calibration procedure. Then the multi-reply questions are, for example, an example of this following one: quantization of a signal converts an analog signal into a discrete signal. This is not true because a quantization signal is not a discrete signal. Converts a digital signal to an analog signal. Of course, this is obviously wrong. Makes a signal assume only a limited number of values. This is what actually a quantization does. So it turns a continuous signal both in time and magnitude into a signal that is continuous in time but is discrete in magnitude. So allows it to vary continuously both in magnitude and time. This is false. Then other examples of open questions. You can describe, for example, different components that are composing the output signal of a real sensor. Let's say the signal, the noise and the disturbance. How do you define the sensitivity of a sensor? What is the dynamic response of a sensor? So there can be an associated question related to that. For example, to measure impact forces, do you think it's better to use a 10 kilohertz bandwidth, so a higher bandwidth load cell, or a 1 kilohertz one? Impact forces have a big spectrum, so usually so that it makes more sense to use a higher bandwidth that is able to read a bigger spectrum of a signal than a lower bandwidth one. And what are the advantages of the issue related to digital implementation of the controller? You remember these are related to phase delay, quantization noise, and aliasing effects. So write whatever, some description about this, and actuators with question examples. Pneumatic actuators are difficult to control, suitable for high force applications. So it's true, the first part is true, they are difficult to control, but they're not suitable for high force application, but for low force application. So this is tricky, that this claim is false. Transform hydraulic energy into mechanical energy. These are the hydraulic ones, so not the pneumatics. Excellent power to weight ratio. Also, this holds for the hydraulic ones, and are useful for application that requires intrinsic compliance. This is true. This is the one of their features. Stepper motor achieve a constant speed for constant supply frequency voltage. This is false because this is not for a stepper motor. Is an AC motor, synchronous motor. And again, this is you need to pay attention. Brushless DC motors have a commutator that provides exciting voltage to the rotor coils, and this is brushed DC motors, not brushless. Actually, the absence of brushes in brushless DC motors allows to remove the need of a commutator. Then other open questions talk about the actuators, kind of actuators in robotics, advantages and disadvantages, function of a gearbox, discuss some pros and cons. In this case, more you write, the better. You need to be careful because there will be many questions and exercises, so you need to really be careful with your time. I think we will allow to keep your material, so you can inspect your material, your slides, but there will be enough questions that if you didn't study, you will not manage to finish in time. Then illustrate different types of DC motors and their applications. Another example is, you remember the optimal gear ratio for power transfer with two inertias, one for the rotor and one for the load. There is a small formula to apply, and then the steady state characteristics of a DC motor. Remember the various parameters like the no load velocity and the stall current, and then no load torque. So you might need to compute the no load velocity for voltages and with the for a certain motor of with a time constant motor constant kV. You need to select the appropriate voltage to be able, for example, to achieve this no load velocity, and also have an operating point that contains the 3000 RPM, which is the velocity, the frequency you want to rotate your motor. Then in terms of control section, some open questions could be describe the difference between open loop and closed loop control and what are the advantages. It's quite simple one. Determine the stability of the linear system represented by the following state space equation. In this case, you need to compute the eigenvalues of the system that are the determinant of the matrix Si minus A, and see if the eigenvalues are have a negative real part. And so the B matrix, you need only the A matrix. The B matrix is put there just to confuse you. It's not did it. Then if you think about a spring mass system, spring mass damper system with parameter MDK, which is a value of D for which the response is critically damped, so as a natural damping ratio of 1. And this is, you remember the formula, just applying the formula 2 square root of Km. Then sketch the anti-wind up schematic and explain which situation is useful. It's another open question. In terms of kinematics, we might ask, for example, a different representation of orientation, the purpose of a rotation matrix, describe which one of the representation of orientation suffers from singularity. You don't need to go too much in detail, but again, the much you write, the more you write, the better. What is a redundant manipulator? So definition of redundant manipulator. It's more degrees of freedom than the task that it needs to perform, and how we take the advantage of redundancy, like to improve dexterity or avoid obstacles. Define what is a kinematic singularity. Whenever, for example, the Jacobian is rank, the more definition you put, the better. So there's a slide that is the slide about singularity. You have 4 or 5 things that, for example, the joint velocity increases close to singularity, and that one's basically. This is the most common type singularities, like the boundary or the internal one. You can even provide examples here. Dynamics. So the question, for example, is about static. Statics investigates, exploits the principle of virtual work to find a mapping between Cartesian forces and joint torques, and this is true. Provides a description of the relationship between the motion and the causes of the motion. This is which are the forces. This is the definition of dynamics. And exploit the principle of virtual work to find a mapping between Cartesian forces and joint torques with the assumption of quasi-static motion. This is the question, the tricky question. That is to make you a problem. And in essence, quasi-static motions. So when you talk about statics, there is no motions. There are just infinitesimal motions to derive the principle of vector work, but they are not quasi-static motion. Quasi-static motion means that there are motions that are very slow, but in the case of statics, they are not there. So this is wrong, and allow to describe the motion, but not the causes of the motion. This is the definition of kinematics. So the first one is correct. The inertia seen by the last link of a robotic manipulator is always constant. This is true. We've seen also before. And this is an example of multi reply question that you might need to do some reasoning about. In this case, we have a VR robot. So 3 degrees of freedom robot with rotational joint that moves on a horizontal plane. So there is no gravity. And you have a trajectory that is like this. So in this case, I suggest you to plot the robot. And you see that the first joint is just oscillating with a sinusoid. And the second joint is moving from the 90-degree configuration. The sine goes to 1 whenever, for example, 2 pi, whenever it needs to cover pi half. So it's whenever it's 1/4 of 2 pi, it becomes pi half, which is sine, which is what's 1, and this becomes pi half. So it becomes pi half for t 1/4, and becomes for t 3/4 second becomes pi. No, sorry, minus pi. So it will be either from the vertical position will be either closing or going out and align it. So we'll do this motion. The third one is always at minus pi half. So it's like this. So it's like an L, and this L shape thing you need to think about is going here. So it will be a robot this way, or is going to be like in the most extreme one, it will be an L like this. So in the first question is about inertia seen by the first joint. It's maximum for t 1/4 and minimum for t 3/4 of second. And this is of course wrong because it's the other way around. Actually, whenever it's 1/4, the thing is completely folded and it's closer to the joint axis, so the inertia is minimum, not maximum, while it's maximum for t 3/4. So this is wrong. Gravity torque seen by joint 3 is minimum of t 1/4. We are on the horizontal plane, so this is just a wrong. Gravity torque is always 0. Of course, wrong. Coriolis effects are always null. This is wrong because we have rotational joints, so we have Coriolis effects always there. Only in the case of prismatic joint, we don't have Coriolis effects. And the inertial torques for joint 2 is maximum at t 3/4. So in case of joint 2, the inertia, it's due to the, since the third joint is not moving and is not changing its configuration, the inertia seen by the joint 2 is always constant. But so it will depend, the inertial torque will be just the mass times the acceleration. So it will be the point of joint 2 where the acceleration is higher. And you remember for the sign, you draw the sign, you have a minus sign for the acceleration, and the top, the highest point in acceleration will be whenever you have the second apex, and it is for time of 3/4 seconds. So the point of maximum acceleration. So this was an hard one. Of course, will be counted more. Then some open questions will be enumerate the advantages of disadvantages of a Newton-Euler approach versus the Lagrangian one, of write the expression of kinetic energy for a rigid body using the Koenig theorem, detailing each variable in the formula. Finally, very few another topic, the last topic is the task space control. And this is again another question where you need to think, reasoning. What happens if we set to 0 the torques of a postural task in a robot that is redundant for the tasks that is doing? So in this case, for example, you think about we are controlling the end effector position with a Cartesian PD controller with a 5 degrees of freedom robot. And what happens, if you remember about the lab, is that the robot was moving. It seems randomly, but actually was not randomly moving because so the first question is the self-motion, which is the motion in the null space, is random because there is no attractor that solves the indeterminacy. It might seem true, but actually it's false because the true one is the third one. The end effector tracks the position of the joint and the position, the end effector position, but the joints settle down in a configuration where the gravity forces are balanced by the structure. So you think about like a chain, the robot is like a chain that under the effect of gravity, actually, if you run the simulation, you see the robot is just moving because following the end effector, but is gravity forces are applied and they put the robot in a configuration that if the end effector is not moving, it will be stable and constant. Then the effector is going to singularity. This is not true, of course, because we are controlling the task. The tracking of the end effector is not possible because we have a redundant robot. Again, this is false. Other examples of open questions explain the difference between Cartesian and joint space control. One is wherever we close the loop at the end effector, and the other one is where we close at the joint level. Discuss pros and cons of task-based inverse dynamics over classic joint space control. In this case, maybe let's call it this way. I want to talk about the fact that inverse dynamics is compensating for inertial effects and Coriolis effects and nonlinear effects in the dynamics, and explain what the null space motions are motion in joint space for which there is no motion at the end effector. So we will put this document together with the examples of today in the folder of the PDFs. Do you have any question? Yes, question for the audience. Yes, you can consult the slides during the exam, but there will be a big number of. I mean, the exam will be will have many questions and exercises. So if you need to be very familiar with all the topics of the course. Of course, there will be some topics that are more important than other ones. So we will evaluate differently. You remember we shared with you an Excel document with the weights for each topic. We will probably detail that more, but yeah, you need to study to be able to succeed the exam. I remember that the delivery of the optional question for the Laude, our deadline is being set to 10 days after the exam, so midnight of day 17, and you can deliver a report to us with replying the questions. You can put code and plots and discuss the results. Yeah.
Posso fare due
Certo.
domande? E quanto durerà l'esame?
Com'è?
Quanto durerà?
Non lo sappiamo ancora.
Okay.
We need to think about that.
Ok, e l'altra era?
We need to do it ourselves and then see. It's the first time we do that, so it's something new and we don't know. Below 3 hours for sure.
Yes, because there are many questions.
Yeah.
I see.
Yeah.
And the other is our monitor will be locked or not? Because we cannot see slides or other things.
Yeah.
Before you talk about plot.
Yeah.
What do you mean?
Yeah, so since we in essence we changed our ideas. Originally we didn't think about letting you keep your material. Now it doesn't make much sense to block the monitor, so I think we will remove this constraint. But of course it holds the requirement for the camera to observe you, because you should do your exam alone and not being help from somebody else.
Yes, of course.
Okay, I remember you that I think you might be able to fill in the questionnaire of evaluation of the course. If you like the course, and it's very important for us that you give a positive feedback, because this will really count for the next year course, if we'll do another one, or even a follow-up of this. And so try to be objective and do it.
Yeah, also I would like to add, like, if you have any feedback on things that can be improved, please be detailed on those things, because it also helps us to prepare future courses. So we would really appreciate the feedback. Also, because this course conditions were a bit particular, and we had to adapt along the way. So we would like to know more or less what we did good and what could be improved. And this is really important for us, the feedback.
Yeah. So how many of you that are subscribed to the exam are from the AIS, sorry, the master of the DZ?
I think that we are all of mechatronics.
You are all mechatronics? Okay.
No, sorry, I am an IS student.
Okay. And only you, or there are somebody else?
Today, I think I am the only one.
Okay. Okay, just for us to do an assessment of the participation of the two courses. Okay, very good. And hope, unless you have any questions, that you enjoy the course. Next year, if we do it again, we'll be with real robots. So UR5 robot for real. We will move them with approaches that we saw. And good luck for everything. And if you have any question, yes.
One extra thing that I would like to add, since probably this is the last time that we're going to talk. So we tried to mention a bit about our own research, the kind of topics that we do in the lab. And if you are interested in the future, when you continue with your masters, on working with us and trying to do, even we can try to arrange doing master theses at IIT in Genova, please don't hesitate to contact us. We're always looking for students, smart students, and that like yourselves. So please don't hesitate to send us an emails. We tried to be as open as we could, trying to reply as well as we could. And if you feel like you want to work on legged robots in IIT, at the Italian Institute of Technology, please let us know. We can also try to organize something. Let's see if in the future we could start collaborating as well. So just keeping the door open for you.
Yeah, thanks, Ottavio. Good point. We are always looking for good students. So, and we have possibility to take some not many master students for an internship, but mainly at the moment we have many PhD students, but we do have always two or three ongoing master students, so it's possible. Okay. So again, thank you very much, and see you at the exam. If you have any question, please write us email. Feel free to contact us.
Thank you.
Bye bye.
Bye.